Have you ever stopped to wonder what powers the physics in your favorite video game? Or, how a pilot actually navigates through a powerful crosswind? Well, it turns out the answer is a kind of hidden language that's all around us. And today, we're going to decode it. We're talking about the language of vectors.
I mean, really think about it for a second. That pilot doesn't just need to know how fast the wind is blowing, but exactly which way it's blowing. A game developer, they don't just care about a bullet's speed, they need its exact path. So how do you possibly wrap up strength and direction into one single elegant idea? Well, the answer is this beautifully simple concept that just unlocks a whole new way of understanding the world. It's called the vector, and it all starts with one really simple distinction. Okay, so first things first, we have to understand that not all numbers are created equal. In the world of physics and math, we basically split quantities into two very, very different camps. You've got scalars versus vectors. So on one side, you have scalars. Just think of them as simple, straightforward numbers. Your speed is 60 miles per hour, the temperature is 20 degrees. They only have a magnitude, right? A size. But on the other side, you have vectors. Saying your velocity is 60 miles per hour. North, now that is a vector. It has both the magnitude, that's the 60, and the direction, north. Getting this one difference down is absolutely the key to everything else. So, great. How do we actually write these things down? How do we speak this new language? Honestly, the best way to think about this is like it's a recipe. Those little letters I, J, and K, they're just super simple instructions that mean move one unit along the X, Y, or Z axis. So this whole formula is really just saying, hey, start at the beginning, take A1 steps in the X direction, A2 steps in the Y, and A3 steps in the Z. And just like that, you've built your vector from scratch. And speaking of those I, J, and K instructions, they belong to a really special class called unit vectors. And their defining feature? Their magnitude, their length, is always exactly 1. Their only job is to point. That's it. They just define a direction without adding any length of their own. They're pure direction. All right, so now that we know how to write them, what can we actually do with them? Let's start with the basics, putting them together and stretching them out. Adding vectors is actually pretty intuitive. It's like planning a trip with two parts. So imagine you walk along the first vector, from its tail to its head. Then, right from where you stopped, you walk along the second vector. The resultant vector, which is just the sum, is simply the shortcut, a single straight line from your original starting point all the way to your final destination. Now, what if you multiply a vector by just a plain old number, a scalar? Well, think of it like a volume knob. If you multiply by 2, you double the vector's length, but it points the same way. If you multiply by -2, you double its length and you flip it around 180 degrees. And if you multiply by 0, poof, it just collapses the vector into a single point. We call that the zero vector. Okay, this is where things get really, really powerful. It turns out there are two very different and very important ways to multiply two vectors together. And here is the absolute core difference. The dot product, it basically asks how much do these two vectors line up with each other? And the answer it gives you is just a single number, a scalar. But the cross product, it asks a much wilder question. It asks what new direction is perpendicular to both of these. And its answer isn't a number at all. It's a whole new vector, pointing out into a brand new dimension. So let's look at the first key application here. The dot product has this, well, it's kind of like a superpower. And here it is. It's so simple. If two vectors are perpendicular, meaning they form a perfect 90-degree angle, their dot product will be exactly 0, every single time. This is an unbelievably fast and elegant way to check for right angles. Now, for the other side of that coin, it should come as no surprise that the cross product has its own equally useful superpower. And here is the crucial takeaway. If two vectors are parallel, their cross product is the 0 vector. I mean, just think about that for a second. Dot product equals 0, they're perpendicular. Cross product equals 0, they're parallel. It's just a beautifully simple test. So we have all these amazing mathematical tools, but what are they actually good for? Why does any of this really matter? Well, what happens when we combine the tools we've just learned? If you take the cross product of two vectors and then you take the dot product of that result with a third vector, you get something called the scalar triple product. And what this kind of magical formula gives you is the volume of the 3D box that's formed by those three vectors. And if the volume is 0, well, that's a really neat trick to prove all three vectors are lying on the exact same flat plane. And here's where it all comes together. This is the payoff. Calculating the area of a tilted solar panel, that uses the magnitude of a cross product. Finding the volume of a crystal structure, that's the scalar triple product we just talked about. In 3D graphics, creating realistic lighting means finding a normal vector that's perpendicular to a surface. That's a job for the cross product. And that plane fighting a crosswind we started with, that requires the dot product to see exactly how much of the wind's force is pushing against it. Every single one of these problems is solved elegantly with vectors. From physics and engineering to data science and computer graphics, vectors are the fundamental language for describing a world that has both magnitude and direction. We've just learned the grammar, so I guess the only question left is, what are you going to build with it?